Nomenclature Part 6. Chemical names and formulas for covalent compounds. We'll talk about how to take the formula for a covalent compound and determine the name, as well as how to take the name for a covalent compound and determine the formula. We'll do a review of ionic compound nomenclature and talk about how an empirical formula, which is used to represent an ionic compound, is different from a molecular formula, which is used to represent a covalent compound. Let's start with a review of ionic compound nomenclature. Remember that ionic compounds are made with a metal combined with a nonmetal, or a compound that contains some type of positive or negative polyatomic ion. If we know the formula of an ionic compound and we want to determine the name, we write out the ions, the positive and negative ions, and we do that to identify the correct ions, and then we just name those ions. The name of the ionic compound is the name of the positive ion followed by the name of the negative ion. If we know the ionic compound name and we want to determine the formula, we once again start by writing out the ions, and then we crisscross and reduce. We drop the plus and minus sign. But why do we reduce? Well, it turns out that's really an important aspect of ionic compound nomenclature, and that has to do with the structure of ionic compounds. Ionic compounds are represented with an empirical formula, or a lowest whole number ratio formula. The structure of an ionic crystal, or a lattice, is a repetitive pattern. So we express the ionic compound with a reduced formula, the empirical formula. This is probably easiest to understand with an example. Let's consider magnesium oxide. That's made of Mg2+, the magnesium ion, combined with O2-, the oxide ion. To get the formula, we drop this 2 down by the O, and we crisscross this 2 down by the Mg, and we initially get Mg2O2 as our formula. But 2 and 2 is a ratio that can be reduced. We can do that by dividing both numbers by 2. 2 divided by 2 is 1, and 2 divided by 2 is 1. So now the new ratio is Mg1O1. When we write formulas, we typically do not include subscripts of 1, so we just write that formula as MgO. And what we have is a crystal of ions held together with ionic bonding. An Mg2+, bonded to an O2-, bonded to an Mg2+, bonded to an O2-, and so on, in some type of a three-dimensional pattern called an ionic crystal. Now, the smallest piece of this ionic compound, of this crystal, is known as a formula unit or a single piece represented by that formula. So it'd be just one single Mg2+ combined with one single O2-. That would be a formula unit. Now, it's pretty typical for people to use the word molecule when we're talking about any particle, whether it's an ionically bonded or covalently bonded particle, but rigorously that's not correct. If we want to be really exact about it, we should be using the term formula unit when we're talking about the smallest piece of an ionic compound, and we would only use the word molecule when we're talking about the smallest piece of a covalent compound. But again, it's pretty common practice to be a little loose with that language and use molecule all the time. Now, MgO, the formula, the empirical formula, could represent a formula unit, or could represent a whole crystal, or it could represent a whole truckload of crystals. As long as we represent any number of magnesium and oxide ions in a 1-to-1 ratio. Now, covalent compounds are different. First of all, covalent compounds are made of nonmetals. If you have two elements, they would both be nonmetals. If you see a compound with more than two elements, and they're all nonmetals, it's a good chance that you're going to be looking at a covalent compound. Nonmetals are elements that have high electronegativity, high attraction for bonding electrons, so they end up sharing valence electrons and forming covalent bonds when they bond together, when nonmetals combine with nonmetals. Covalent compounds are not represented with lowest whole number ratio formulas or empirical formulas the way that ionic compounds are. Rather, covalent compounds are represented with molecular formula. That's a formula that's not reduced. So the structure of a molecule is reflective of the exact number of atoms in the chemical formula. Again, it has to do with the structure. Notice that we don't have a repeating structure here in this example. C2H2 doesn't have the same structure as C6H6. Check out these two-dimensional structural formulas, or Lewis structures. These are different structures, and that's why we have different formulas. Notice these are two molecular formulas, not reduced. If we reduce this one, we get this empirical formula. And if we reduce this molecular formula, again, we get this empirical formula. So these are two different substances with the same empirical formula. Two different sets of properties, completely different chemicals. So we can't reduce covalent compounds. They don't have repetitive structure the way ionic compounds do. So how do we name covalent compounds? Well, the good news is that it's a lot easier than ionic compounds. All we have to do is make sure that we use Greek prefixes, and remember to skip the prefix mono when it's on the first word. Here are the Greek prefixes. Mono is 1, di 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. Here are a few examples. N2O4. In English, that's 2 nitrogen 4 oxides. In Greek, dinitrogen tetroxide. Di is 2, tetra is 4. So 2 nitrogen 4 oxide, or dinitrogen tetroxide. Here's another example. CCl4 is the chemical formula. Notice we have 1 carbon, but we don't write 1 when we have a subscript as a 1. So carbon tetrachloride is the name. Notice how we skipped writing mono on the first word, right? We got to skip doing that. And the prefix for 4 is tetra. So 1 chlorine, or I'm sorry, 1 carbon, 4 chlorides is carbon tetrachloride. Skip mono on the first word. Here's another example. You're probably familiar with this element, or this compound rather, carbon monoxide. Notice we don't have a prefix here in front of carbon, so that means there must be just 1. We skip mono on that first word. But we do include mono on the second word. Monoxide means 1 oxide. So we skip mono on the first word, but not on the second word. Carbon monoxide is a good example to remember for that. And then check out this example, disulfur heptoxide. The formula would be S2O7. Now, I want to point this out because it can be a little bit of a confusing thing for students. Di modifies sulfur, so there's 2 sulfurs. The 2 subscript modifies the S. So the di prefix comes before the word, and the 2 subscript comes after the symbol. Be careful about that. Notice that hept, the prefix for 7, comes before the word oxide, but the subscript 7 comes after the symbol for oxide. All right, so we can follow this general pattern. We have a prefix for the first element, and then we give the name of that element, and that would be the least electronegative element. Now remember, electronegativity is small on the lower left-hand part of the periodic table. So this would be the element that's farthest down and to the left. That's kind of easy. The element to the left in the name for the compound is the element that's farthest to the left on the periodic table. Then we put the prefix for the other element. So here we have di, sulfur, and then hept is the prefix for the other element. We put the stem of that more electronegative element. Oxygen is farther up and to the right, so farther to the right in the name, farther to the right on the periodic table. The stem of oxygen is ox, and then we just change that suffix to IDE. Notice we did that all along here for that second word. Ide, 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 ide. So we have prefix di, name of the least electronegative element, sulfur, prefix hept, the stem of the more electronegative element, ox, and the suffix ide. Now that's a pattern I would suggest you not try to memorize. I think instead, just by doing some practice, you can pick this up. There is one point I'd like to make, and you maybe have noticed this. We sometimes drop a vowel from the prefix. Notice that CO is carbon monoxide. We don't call it carbon monoxide because reading that out, you might be tempted to write that as monoxide. So what we do is we sometimes drop a vowel in the prefix at the end of that prefix to avoid that weird kind of a pronunciation thing. That's not really something to get too worried about. Again, through usage of the names, you can pick that up. It's probably best to learn a new language and the vocabulary of a new language just by, getting in the lab and practicing and becoming familiar with the chemicals. So let's say that if you understand everything that we did in this video so far, you should be able to give the covalent compound names and formulas depending on what's missing for these 10. So for the first 5, I'm going to give you the formula. You give me the name for SiO2, N2O5, CS2, SF6, and P4S3. And for the second 5, numbers 6 through 10, I'm going to give you the name. You give me the formula. So oxygen difluoride, xenon tetrafluoride, diphosphorus pentoxide, trisulfur dichloride, and tetranitrogen trioxide. Remember to use prefixes, the Greek prefixes that we went over, and skip mono on the first word. And also be careful that ionic compounds have a different naming system than covalent compounds. So with covalent compounds, we don't write any ions out. There's no ions involved here because we're sharing electrons, right? We're not trading electrons to make ions. And there's no crisscross and reduce involved. You just take the subscript and interpret it as a prefix. Again, skip mono on the first word. Or if you know the prefix, like di, interpret that as a subscript. All right, good luck.